Okay, so so Michael was asking me whether I'm going to talk about my old duality ideas for quantum gravity, and I sort of am, but what I've been doing in the last 10 years is to try to come back to more practical things, to come at it from a more realistic side, because big ideas and big philosophies, you also have to complement them by specific results. So anyway, coming out of that whatever philosophy there was there in the 80s, we have this quantum spacetime hypothesis. So this is just if you like, it's a philosophical position that the real world, spacetime, is better modeled by a noncommutative geometry where your spacetime coordinates do not commute, that is a more realistic description of the world than classical geometry. So that is my starting philosophy, if you like. There are deeper origins to that, which I just touched upon. But for our purposes, that's where we're going to start. Now, so that is now widely accepted. So we don't know what quantum gravity is, but it's now widely accepted among quantum gravity, most of the quantum gravity community, that whatever it is, the modifications of quantum gravity will be first seen, or will be visible, as a modification to classical geometry with quantum corrections. And those quantum corrections could be expected to take the form of non-commutation relations between coordinates. So this gives you a mathematical challenge of formulating geometry in a way which allows the coordinates of space and time to be non-commutative, to be operators, as in quantum theory. So this is now largely achieved over the last 10, 15 years. It's what I would call quantum Riemannian geometry, or non-commutative Riemannian geometry. And then, of course, in the limit, as the deformation parameter, that's Planck scale parameter, goes to 0, we should recover classical geometry. So that's the assumption. We don't know what this is. We do know what this is, and we're making a hypothesis that as the Planck scale goes to 0, theoretically, as quantum gravity effects become negligible, this theory will factor through an approximation, which is this one, on its way to the classical limit. So that's our starting assumption. Now, interesting. Now, that happens. Okay, I sort of keep moving. Okay, fine. Now, the one thing that's been discovered is that if you accept this philosophical position, this hypothesis, you discover that actually this map is not surjective. So not every classical geometry can arise as the limit of a quantum geometry. Quantum geometry turns out, because of the non-commutation relations, it's more rigid than classical geometry. And so the idea is that some of the things that we observe in classical geometry, I mean, not every classical geometry, is physics. Some of the things that we observe in the real world have their explanation not within classical geometry because they would not be constrained, but they have the explanation in the existence of the quantum geometry. In other words, there are quantizability constraints on classical geometry which have to hold if this hypothesis is correct. If classical geometry is the limit of a quantum geometry, there will be remnants of that information which will be quantizability constraints. Okay, now I'm going to illustrate this with an old algebra that Ruegg and I introduced in '94, which is this one. So this is the simplest and most studied model of quantum space-time. So you have x1, x2, x3, and the time coordinate, and they don't commute. And here is the Planck scale. So this here is this is 10 to the minus 44 seconds. So that's just obviously just a model. It's just an example of a possible model. There is evidence for this kind of model in 2+1 quantum gravity. Now, what I'm going to show is that, which is recent work in the last couple of years with collaborators, Edwin Beggs and my student Tao. What we've shown is that, in fact, this very simple algebra has an intrinsic geometry. It's forced on you just out of this algebra. So knowing nothing but this algebra, we will be led, and this philosophical position, will be led to the Bertotti-Robinson solution of the Einstein equation, which is a certain metric on Sn cross ADS, antidissociative space, or depending on a choice of differential calculus, which I'll explain, to an expanding type universe. Now, so apart from this algebra, there is the question. The reason there are two possibilities is you have to choose the differential structure. So we know what x is, but what is dx? Dx is the differential structure. So in our geometry, we replace the manifold by an algebra, which is like the topology of the space in some sense. And we have to have something which encodes the differential structure in order to do physics. And so we have to encode the Leibniz rule. And that encoding algebraically is the choice of differential structure. And then you discover that actually, when the algebra is non-commutative, you have, actually even classically, you have more than one possible differential structure on a topological space. And that is the same with algebra. So even this algebra has more than one differential calculus. But if we ask for ones which are translation invariant, then classically there's only one. For this algebra, there are two, plus essentially two. Okay, so there's obviously something going on here with this constraint and with these solutions. So then the rest of the talk will be devoted to the general theory of analyzing this situation. And that is what I call Poisson-Riemannian geometry. So understanding the quantizability constraints on classical geometry. So it means a classical manifold equipped with a Poisson tensor and a metric. Okay, so before I do that, I'll just refresh some people's memory about this old algebra. So this old algebra people first looked at it from the point of view of some kind of Minkowski space. And it was just an assumption that it's because it has a quantum group which looks like the Poincare group, people thought this must be Minkowski space. So it's sometimes called kappa Minkowski space. On this space there, you can write down waves like this. Even though x and t don't commute, you can still write these down. And you can write down a very natural wave operator, and these are eigenfunctions of that. And then when you look at the sort of natural wave operator in that context, you have this relation on the momentum space. And this is the deformation of the usual p squared minus p0 squared. And so that means that when you look at the dispersion relation, which is this, when you differentiate it to get the group velocity, you get something which has a speed, an energy-dependent speed of light. So this is the kind of this is the only model that I know, actual model as opposed to speculation, which predicts variable speed of light. And this was studied in this paper with Amelino Camiglia. And in fact, even though lambda is 10 to the minus 44 seconds, we are not necessarily in the realm of pure speculation, unlike some branches of theoretical physics, because even this prediction could be tested and disproven using gamma ray burst data. There's been one big gamma ray burst a couple of years ago, which people think might even disprove it, but you really need to have a lot of data before you can analyze it statistically. So I'd say it's still open. Another thing you can do with this differential calculus, with this algebra, is, as I said, you have a choice of differential calculus, which also reflects changing the wave operator. And in particular, it turns out that flexibility can be used to encode Newtonian gravity, for example, a point source. So you put the point source background into the wave operator, and then you apply the usual approach to go from the Klein-Gordon equation to quantum mechanics, and you get this limit in the limit of slowly varying field psi. And what you discover is that you get something like Schrödinger's equation, but firstly you get a kind of vacuum energy, and secondly, the gravitational mass, the effective mass that goes in, the thing that goes in here, mg, is no longer m. Even though m was the mass here, this mg is no longer m. There's a graph here about how they behave. And this mi also is no longer m. So the inertial and gravitational masses split off from the Klein-Gordon mass. So this suggests some very interesting behavior of quantum mechanics as you approach the Planck scale due to non-commutative geometry. I should say this is purely speculative. I mean, it's just a model. I don't know that this particular model is right, but it illustrates possibilities. Another thing you can do is to modify the wave operator to match the one for a Schwarzschild black hole. This is in this paper here. And then you discover something similar, something nice happens, which is that the time dilation factor from where we are to the event horizon actually depends on energy. And so time dilation becomes energy dependent. And what's more, unlike the classical calculation where that factor blows up as you approach the horizon, in our case that factor is finite. So you don't have a sort of radiation, a sort of singularity in the redshift as you do classically. So here is the red one is the classical wave as it gets more and more compressed as you approach the horizon. But when you solve it for the quantum wave operator, it's perfectly fine. It's perfectly regular at the horizon. So again, it could be an artifact of the model, but these are just some models. Now, another thing which I mentioned briefly was this idea that somehow vacuum energy could appear as a quantum correction. So the idea would be that that a non-zero cosmological constant, which is something that we need to explain, any decent theory of quantum gravity has to explain why we have a value which is so small compared to the Planck scale and yet not zero. And so the idea for that would be that it is, in some sense, zero, but it becomes non-zero due to quantum gravity corrections. And that then explains, or can explain, why it's so small. Now, I should say that these are all relatively old works, and this approach, it's a nice one, but it is somewhat ad hoc, and it is based on wave operators rather than the actual noncommutative or quantum Riemannian geometry, which I had promised you. So what I'm going to do now is just to put that historical thing aside and look at some actual mathematics. So I'll keep the mathematics very brief, but I've given you the philosophy. Now I will give you some maths, and then we'll go back to the philosophy. Okay. Now, the tiny bit of mathematics is what is differential structure on an algebra. So A is an algebra, possibly non-commutative. The differential forms, like things like dx, I will sort of abstract their properties. And so by definition, a differential form means, a space, omega 1 of such differential forms. And this omega 1 should be an AA bimodule. That means I can multiply a differential like dB from the right or from the left. And those two operations should commute. This is what's called a bimodule. So omega 1 should be something that you can multiply by functions. You can multiply a differential form by a function from the left or the right. Then, there should be a map D from functions into differentials. So A goes to dA, and this should obey the Leibniz rule. So we have just captured the essence of differential calculus, and nothing more. We're making very few assumptions. And then we should, of course, we would like omega 1 to be the space spanned by such things. Otherwise, we would just take omega 1 to be smaller. And classically, for a connected manifold, the only thing that's killed by D is the constant function. K is the field. So in our case, we would be interested in connected calculi with the same property. Typically, we'll extend omega 1 to differential forms of all orders. We'll take a kind of tensor product and then quotient by some relations to get a differential graded algebra. I won't go there very much today. The thing of interest to us for Riemannian geometry is a metric. So a metric is an element of omega 1 tensor omega 1, right? It's a 1-1 tensor, 1-1 form. And tensor product over A is what tells you that it's g mu nu of x with only one x. If it didn't put the tensor product over A, it would be g mu nu of x comma y for two different points. But in tensor calculus, in geometry, we're always working, without necessarily realizing it, in the tensor product over the algebra. So that's what we encode there. It should be symmetric in the sense that the wedge product, this wedge product here, should kill g. So that's a kind of symmetry. And it should have an inverse, which is the inverse metric. It will go the other way, a map from one form to tensor one forms into the algebra. And this should be a bimodule, so it should commute. This is tensoriality. If I give you an operation like this, which is tensorial, then it means it commutes with multiplication by functions. So that's what you would want. Now this, in noncommutative geometry, this very innocent requirement turns out to force the metric g to be central. You can show that if an inverse exists, then g has to be in the center, has to commute with functions. So multiplying by a function here, you can take it through to the other side. And that is a very strong constraint. So we see already the rigidity of noncommutative geometry, and yet I haven't really assumed anything. I put it to you that I've only assumed the bare minimum. I've assumed that the algebra is noncommutative, possibly noncommutative, and then I've just taken the very minimum for differentiation and a very simple requirement for the metric. I don't think you could reasonably avoid these assumptions. And yet we find this rigidity coming from the non-commutativity, the centrality, which of course is not a restriction classically. Okay, then the last thing we will need is a quantum Levi-Civita connection. So this will be a map from omega 1 into omega 1 tensor omega 1. Now you don't normally think of a connection like this. You think of a connection as a covariant derivative. For every vector field, you have an operator on omega 1. But if we leave that vector field unfilled, so then this is what this is. this is a map from here, and this element here is waiting to evaluate against a vector field. So this nabla is the totality of all possible covariant derivatives along all possible directions. So that's how we think of, I knew this would happen. That's how we think of a metric, of a connection abstractly. And we would like this to be metric compatible, and we would like this to be torsion free. Now torsion turns out to be very simply this. If you take this and apply wedge, you go from omega 1 to omega 2. And if you compare that with D, that difference is the torsion. So I would put it to you again that actually all the formulae in books on Riemannian geometry are much more elegantly written as algebra. But that's just my personal view. Okay, now just a simple example. We have that same algebra that I mentioned here, the by cross product model. As the algebra, but here's an example of a differential calculus. There are only two main, you can classify the calculi, and there are only two translation invariant calculi, essentially. And this is one of them. It has a parameter alpha in it. And so differentials don't commute with functions. And this is the rule. And then you write down a general possible metric, and requiring that centrality that I told you, requiring this forces this particular pattern of degrees for these coefficients. And then when you combine that with spherical symmetry, you discover a unique form of metric. So there is only one possible metric on this algebra that is rotationally invariant, which, you don't have to assume it's rotationally invariant, but it's a reasonable simplifying assumption. So if you assume that, you are forced to this metric. And this metric in the classical limit is the Bertoldi-Robinson metric. So these parameters, you can change coordinates. The thing that's really relevant is this combination, where delta is bigger than 0. And the Einstein tensor then of this metric classically works out like this. And it's known that this solves Einstein's equation with a Maxwell field. This is the Maxwell field, and with the cosmological constant. So depending on the value of delta and delta bar, you could have lambda to be non-zero, to generically be non-zero. But what's really important is that it is really just forced out of the algebra and some very minimal philosophical assumptions. Okay. The other possible calculus is this one. This is the beta calculus. It looks a bit more complicated, but the standard one, discovered, I should say, by Sitash from Kraków, in the case beta equals 1, would be here. So we'll look at that case, beta equals 1, and we'll look at the 2D case. So to keep things simple. So then there's just one variable x, which I'm calling r. Then again, there's a unique form of metric, which forces you to this metric with one parameter b. And in the classical limit, this metric is a certain conformally flat metric with a Ricci singularity. If b is less than 0, then the geometry of this metric corresponds to a very strong source at the origin. And they are plotted some geodesics. These geodesics sort of oscillate. Well, they don't oscillate. They go from this point back all the way back to this point here. I mean, you could continue them. But they correspond to a very strong attractive force at the origin from the Ricci curvature. The other choice, if b is bigger than 0, is that you should change variables so that you have the time signature correct. Then you have this metric, which is an expanding universe metric of some kind. And here, again, there's a Ricci singularity at t tilde equals 0. I don't want to spend too much time on this. It's just this is in this paper. Okay. So again, the point is that with minimal assumptions, we were forced to this. Okay. So now what I want to really talk about today is what's going on with these models. Why are we being forced to these quantization constraints, and how can we analyze it? So I'm going to look at this mathematically, but I'm going to simplify by looking at quantum deformations, but so with quantization parameter lambda, but only working to order lambda squared. This is the semi-classical theory. Now, everybody knows that the commutation relations at semi-classical order are controlled by a Poisson bracket, which is a Poisson tensor. But the new ingredient in noncommutative geometry is that the differentials don't commute. So we have another tensor, another object, which is the thing that controls the non-commutativity of the differentials. So A dB minus dBA. The failure of the differentials to commute is another tensor. It's not the Poisson tensor, it's something new. And I'm going to call this nabla. and it required to obey these conditions. And you can see this looks like a connection along direction of Hamiltonian vector field. This would exactly be a connection. So this is a partially defined connection defined along Hamiltonian vector fields, and it's required to be Poisson compatible. And those two, this comes out of the Leibniz rule, and this gives you your commutation relations. So now it turns out that this connection, if you compute the double commutator, the Jacobi identity would correspond to this being 0. So if your calculus, if this was part of a noncommutative geometry with an associative differential calculus, in other words, obeying the bimodule condition, for example, to all orders, then at order lambda squared, you'd be forced to have 0 curvature. However, we are going to work in what is a new paradigm of physics. This paradigm of physics is physics at order lambda. Now, if lambda was the Planck scale, if lambda was h bar, this would be classical mechanics. But lambda isn't h bar. Lambda is the Planck scale. So what does it mean to study semi-classical physics, so order lambda physics, which is a kind of classical mechanics of some kind, but the parameter is not h bar but lambda. This means a paradigm of quantum gravity, of classical quantum gravity. And there's even a journal where you can publish such results. Okay. At this order, lambda, we don't care about flat because this non-associativity problem occurs in the future. It's order lambda squared, and it may be that the real world is non-associative. And we shouldn't, since it's very hard to measure Planck scale effects, it's even harder to measure Planck scale squared effects. So for our purposes, we shouldn't assume that the world is just because it's mathematically nice, we shouldn't assume that. So we have a new field in physics which controls the differential structure. And this new field is a connection, a gauge field. And this connection could have curvature. If it has curvature, it corresponds to non-associativity at a higher order. And the question is, what is the physics, or what are the field equations for this new field of nature? So just summarize, the philosophical assumption that space-time as we know it is the limit of a quantum space-time implies the existence of a new field, a new gauge field in nature, which controls this non-commutativity. Now, what are the field equations of this new field? So these are the equations of what we call Poisson-Riemannian. We're interested in the case where the manifold has a metric. So far, I didn't mention the metric. So now suppose the manifold has a metric with Levi-Civita connection, nabla hat. Then what other conditions? I've already told you some conditions on nabla. It turns out that one requirement for G to be quantizable is, well, you probably guessed it, G should be metric compatible with this connection. So this nabla is my new field, this new gauge field that controls the differential structure. It should be metric compatible. Now, if that's the case, then we could write it as a difference from the Levi-Civita connection by the contortion tensor. And the contortion tensor will be determined from the torsion of nabla. So in fact, I'm going to regard S as the field, as the new field. Because of this first field equation, I can regard S, the contortion tensor, as the new field. It's easier to work with tensors than it is to work with connections. And if that holds, then it turns out you can quantize the metric to order lambda. And this is the quantum metric. So I won't worry about what Q is. It begins the classical metric plus quantum corrections, given by the curvature and torsion of nabla. Okay. Then we required that Poisson compatibility with the Poisson bracket. In terms of S, this turns out to correspond to this equation here. So this says that the covariant derivative of omega, of the Poisson tensor, by the Levi-Civita connection is controlled by S, well, this equation. And this actually implies integrability conditions on the Riemann curvature. So we are getting constraints. In an ideal world, I would like to get Einstein's equation or something like this out of such a condition, but we haven't got that. But we have got some kind of constraint on the curvature of the Levi-Civita connection coming out of the existence of the quantizability because of the integrability of this equation. Now, the third equation of Poisson-Riemannian geometry is this one. And this is the condition for the existence of a quantum Levi-Civita connection. So I told you mathematically what I've been talking about, what a quantum metric is, what a quantum Levi-Civita connection is. We can analyze what it takes to get those, and this is the condition that we need at order lambda. And it's the paper with Beggs that I'm talking about. I should have mentioned that. This paper here. It's a 50-page paper, but we analyze all these things. So now this tensor R is a two-form, which we call the generalized Ricci two-form. So on a Kähler manifold, you wouldn't have this term here. You would have this would be the Ricci two-form on a Kähler manifold. So, but we haven't got a Kähler manifold, but we have got omega, so we can make this contraction. So that has to be the covariant derivative of R has to be equal to this, has to be controlled. So those are the three equations. If you can do that, you have your quantum geometry at semi-classical order. And the first thing you could do is to write down the wave operator. So the wave operator would be apply D, apply the Levi-Civita connection, and apply the quantum one, and apply the quantum inverse metric. That's how you could reasonably expect to define. We follow the geometric recipe for defining the Laplacian but now in the quantum case. If you do that, then you can compute it, and it turns out to be the classical one plus a quantum correction. So this is the first prediction of Poisson-Riemannian geometry. Those were the field equations. This is the first prediction. That the wave operator, which controls everything, controls all the physics, as I showed you in examples, that wave operator gets modified, has a quantum correction. This is the Ricci curvature of our new gauge field, of our new field of physics. It's Ricci curvature. And actually, this is the covariant derivative of the contraction of the contortion tensor. That's also built from our new field. And it's that contracted with the covariant derivative over here. So I don't know what it means, but this is a very substantial calculation in the paper, plus order lambda squared. Okay, so I just have a few minutes left, maybe 5. So I should say that I'll just say a little bit more about this. That if this equation doesn't hold, you still can do things. So it's not like what happens is you have a natural nabla 1, and the symmetric part of nabla 1 on G1 vanishes. Now it turns out, if you do the calculation carefully of the classical Levi-Civita connection, the thing which determines the Levi-Civita connection is actually only the symmetric part of nabla hat on G. Because nabla hat, the Levi-Civita connection on the classical metric, is already symmetric. So there is no antisymmetric part. But in the quantum case, there could be an antisymmetric part. So, and that we can always solve. So we can always get the symmetric part to hold, which is what you would see classically. There could be a non-symmetric part, and this is the vanishing of that. If this doesn't vanish, then you have another quantum effect, that the metric compatibility has an antisymmetric part which doesn't appear classically. So I don't want to necessarily put all my bets on one horse. It could be that's an actual effect, order lambda effect, which I have glossed over here. I've eliminated it by requiring this to be 0. Okay. Now, there's a lot we can do with this. So I've got the equations. The first thing I've done is with a student from Sussex, Christopher Fritz. The paper appeared in November. And what we analyzed was what those field equations amount to in the case of a spherically symmetric spacetime. So it's a four-dimensional classical spacetime with arbitrary coefficients A, B, C, which depend only on R and T. So a general spherically symmetric spacetime. And what we found was that for generic values of A, B, and C, there is actually a unique solution to the field equations. So what I'm trying to say is that in the first part of the talk, I showed you some models where I fixed the calculus first, and then I found the unique metric. I found a unique metric. So I fixed the calculus first. I fixed nabla, and then I found a unique metric obeying this equation and these other equations, which held anyway. So there we fixed the metric, and we were forced to G. That was the quantizability condition on G. Now we're doing it the way around. We're fixing the metric, and we're going to regard the new gauge field, which determines the nabla, as the thing we were going to solve for. You're solving a joint system. You can take whichever point of view you prefer. So it turns out if you insist on having a spherically symmetric metric, and if you insist on omega being spherically symmetric, so it's a spherically symmetric quantization, then there's a unique solution for S. Essentially, I mean, there are some unphysical degrees of freedom in S which don't show up in the calculus, and they aren't determined. But all the physical degrees of freedom of S are determined, and this is the solution. And as part of this process, we find that R and T and dr and dt have to be central, so they commute. So they are unquantized. So this is a non-quantization theorem for radius and time in a spherically symmetric situation. And but at each class, so they're kind of classical R and T, and at each R and T, you have the angular degrees of freedom, and they are quantized. And this is what we call the non-associative fuzzy sphere. So it has three generators, Z1, Z2, Z3. They correspond to the angular variables because Zi is xi over r. So they're the Cartesian angular coordinates. They obey this relation. And they have this uniquely determined calculus. So they have a non-commutation relation which you'll recognize as the angular momentum algebra. So the spin network, well, the angular momentum algebra of M algebra SU2 appears forced out of you, forced on you out of nothing but out of the field equations and the assumption of spherical symmetry, and you're forced to this calculus, which is a very weird calculus that I certainly never seen before, and it is non-associative at order lambda squared. Now, of course, one special case is the Schwarzschild black hole, and that's spherically symmetric, so you can do all the calculation for that. And then you can compute the quantum Ricci tensor. So this is the Ricci curvature of the quantum Levi-Civita connection. And you find out it is 0 at our level. It's order lambda squared. So that property of the Schwarzschild black hole is preserved, as we might expect. And that's as far as the general theory is concerned. As you can see, it's very new. But the framework is now a couple of years old. And there's a number of models being investigated. I just wanted to return back to the philosophy briefly, and then I will finish my talk. So going back to the philosophy, if lambda was h bar, then what have we done? We've looked at the conditions for quantizing a metric on phase space. And so you might well ask, why do I care? Why do I care about the geometry of the classical phase space of a mechanical system? Because that's what we're doing. We're doing order lambda. So we're actually doing classical mechanics. But the non-commutativity has remnants. One of those remnants is the idea of an inner automorphism, which means a commutator with h. And that translates into everyday language as the Hamilton-Jacobi equations. So Hamilton-Jacobi equations are an example of the philosophy that, I mean, I'm obviously repeating history, that classical mechanics is the limit of some quantum mechanics. But what I'm saying is that we have the possibility of not just of commutators, but of geometry on the quantum phase space. And so what are its consequences? Then at the moment what we can say is that there are constraints on that geometry. So for example, if you, you can solve these conditions for CPN, and so certain geometries will appear as quantum phase spaces, and certain other ones won't. So you've got these conditions. And going back to some philosophy about duality, geometry of phase space has two parts, the position and momentum. But because we're doing everything geometrically on phase space, when you're doing Riemannian geometry on phase space, you are doing curvature on space and curvature on momentum in a completely symmetric way. And so what these equations are that I've told you, when applied in this context, is they are the semi-classical way to explore some old duality ideas of Born reciprocity, of position momentum duality, which I know has inspired Michael as well as myself. That's one possibility. The other possibility that I mainly talked about is that lambda is Planck scale. And in this case, as I mentioned, what we have is something uncharted. It's not classical mechanics anymore, but it has the methods of classical mechanics. We have Poisson brackets, but now we have this connection, this Poisson connection, but it is actually quantum gravity phenomenology. It's the study of quantum gravity effects at first order in quantum Planck scale. So that is a new approach, if you like, to quantum gravity, which is what we could call semi-classical quantum gravity. Okay, and so I would like to stop there and to remind everybody, in case you don't know, that this is the birthday year of Michael Heller. Thank you.